Hi, this is Tom, and in this video we're going to continue with the central limit theorem, and here's what we're going to do next. I'm going to go grab our picture that we made earlier at the very beginning, and here it is. So we're going to use that, copy that, and bring it down below, put it right here, how about, paste, and I'll probably make it just a little smaller. It doesn't need to be too bad. How about there? And then we're going to come up here, and I want this frequency distribution as well. I'll show you what we're going to do with this. Okay, let's put that down here and make it a little smaller, because we're going to use that little piece. Actually, let's pull it over here. Okay, now let's graph our frequency distribution. Now we're going to make a histogram for that, and we'll use another color. And we'll use this pretty blue. Now notice this. Notice that we have data values now, not just at 2, 4, 6, and 8, but we have ones at 2, 3, 4, 5, even a 7. So let's graph these. So it says here at 2, we have a height of 1. So I'm only going to go up to, I'll split the difference between the 2 and the 3. And there's the first bar. And then it says for 3 I'm at 2, so I'm going to have to go all the way up to 2. I'm going to bring my 2's over a little bit. I might have to use those. So 3 goes all the way up here. And then 4, that one goes all the way up to 3. So 4 goes up to 3. 5 goes up to 4. So 5 goes up to 4. The 6 goes up to 3. The 7 goes up to 2. And the 8 goes up to 1. Wow, and look at this picture, because here's what happened. The pink, when we started this problem, we had the pink one down here. This flat histogram is called a uniform distribution. It's called a uniform distribution. But look at what happened. When we took all the possible samples of that data set, and then we took the sample means and we graphed the sample means, we get this beautiful normal distribution. Well, wait a minute. So you might wonder, well, why is that so important? Because here is what's going on. Notice that when we started with the uniform distribution, then there's really nothing special about it. For example, none of the work that we've done with a normal distribution would apply. But if we wanted to study groups of the uniform distribution of size 2, or actually groups of any size for that case, then what we would know is if we looked at all possible groups of the same size, that then our data works like a normal distribution. The empirical rule applies, z-scores apply, and everything we've been practicing can now be used right here based as a normal distribution. And that's the idea of the central limit theorem. The central limit theorem takes all possible samples that's a P, all possible samples of size n, and the result is a normal distribution with the mean of the samples, oops, I wrote that one kind of strangely, the mean of the samples equal to the original population's mean, and if we know the standard deviation of, and the standard deviation of our new one is no different than the populations, except for that you divide by the square root of n. And that is what we can use now to find any kind of problem from any kind of distribution. So let's try an example here. Here we go. Is that what I wanted? Okay, that's what we're going to do. So consider this. For example, find the probability that z, so z is between -1 and 1 for, this is just a normal distribution, so mean is 0 and standard deviation of 1, for a group, or for groups of size n equal 4. Okay, so let's try this. So now, if I have a normal distribution, well, this is a picture that we've worked with many times. And we know that the mean goes right here in the middle at 0, then 1, 2, and 3, and 1, 2, and 3. Now, we also know this. We know the empirical rule would tell us that about 68% falls between these two yellow lines. But wait a minute. The picture has changed now because we have a groups of size n is 4. So our blue picture has a standard deviation of 1. But what we're going to do is we're going to create an orange picture, and this one has the standard deviation equal to 1 divided by the square root of 4, the sample size. Well, that's 1/2. So wait a minute then. So if I put 1/2, let me finish this. Here was our 1, our 2, and our 3. -1, -2, and -3. So notice this, 1/2 would be right there. And then for this new curve, 2, or this is now the new 1. For my new curve, the standard deviation is 1. So for my new curve, this is 1 standard deviation. This is 2. And this is 3 right there. So if we go the other way, it would look like this. And so now, when we graph this, instead of having it spread out like it is, you see here, instead what happens is the picture gets squished, but the area under it is still 1. And so you get this picture that gets really pushed up. So notice that now pretty much all of the area is in a very tight little range. And so now if we want to find between z being -1 and 1, we're looking at all of this. So it's a much larger region. So we could do this on our calculators. let's do this. So now if I look up z, actually, if I look at this up, so z equals, now what I would do is my data value now is 1. So I go 1 minus the mean, which is 0, and then I'm going to divide it by my new standard deviation, which was 1 over the square root of 4, or 1/2. So I take 1 divided by 1/2. Well, this is 2 now. And see how that matches with what we found above. And my other data value is z equals -1 minus the mean of 0 divided by the 1/2. So that's going to give me -2. And so now, if I was to look that up on my tables, so I'm going to look that up on my table, then what would I do is I'd have to come back. So let's go back to our statistical tables here. And if I want to look up -2, well, -2 is going to be right here. It's 0.228, and I'll have to remember that, hopefully. And then if I look at +2, it's 9772. 9772, 0.228. So let's come back to where we were and see what we've got. So now the area for this one, oops. The area for this one was 0.0228, and for the +2 it was 0.9772. So the area in the between the orange, the total area in the orange, is the difference of those. So if I take the 0.9772 and I subtract 0.228, then taking my TI-84 here, let's put that in. I get 0.9544. So now it's taken all the data that used to be between 1 standard deviation above and below, and it squished all of that into the space of just 2 by only taking groups of just size 4. So I have one more example for you, but we'll do that in the next video. Thanks for watching.